This is Pwn Rope Dancer. This was my favorite challenge as part of the CTF. If we take a look in Ghidra, we can see this is actually hand-rolled assembly. And it's just doing a bunch of syscalls, moves, XORs. There's not really that many gadgets. But anyways, the way this program works is it accepts two different buffers. The first buffer is supposed to be an email, but it's a buffer overflow. And I think it overflows by maybe like 32 bytes or something like that, so we have enough room for a couple of gadgets. The second buffer is not an overflow. We're just going to be writing to a known address in the read-write section, and I think we get OX 500 bytes. Plenty of data to store stuff. Oh, actually, it's right here. It's just 500 bytes straight. So, pretty fun, but like I said, we have that buffer overflow, so we can start ROPing. But what makes this challenge tricky is there's not a lot of good gadgets, and there's no obvious targets. There's no libc. And most of the instructions here are just like moves and mostly just moves and XORs and stuff. So somehow using a single buffer overflow with 4 or 5 gadgets and then this buffer, we need to get shell. So to do this, there were 2 very fun tricks that I haven't used in a while, and I think this is why it was my favorite challenge. The first trick we're going to be using is a stack pivot. Like I said, the gadgets are very constrained, and there just isn't enough room to do what we want using only 4 or 5 gadgets, with only enough space for 4 or 5 gadgets. But we have that 500 byte buffer. So what we're going to be doing is first a stack pivot, so that instead of the stack pointing into some high stack address, we're going to overwrite that 500 byte buffer with a bunch of ROP code, and then we're going to point the stack to that 500 byte buffer. So we can do as much ROPing as we want. And the second tool is, like I said, we're just very constrained in this program. There just aren't that many gadgets to use. We're going to use something called a sig return. And so a sig return is a syscall. I think it's syscall OXF. And what's fun is, so this is used when you're returning from signals. This is used by the operating system. Basically, the operating system will store a whole bunch of context on the stack. And when you call the sig return, it'll pop all that information off the stack and fill in the registers. And so you can use this when you're in a constrained environment to set the registers to everything you want. The trick is you have to have a lot of stack space, like 300 or 400 bytes or something like that. Thankfully, since we have 500 bytes, we do have enough room to do something like this. So the idea is, one, we're going to do the stack pivot, move the stack over to the 500 byte buffer, and then in the 500 byte buffer, we're going to do a couple of gadgets to set everything up so that we can do a SROP. And then from there, we're going to call SROP, set all the registers and values such that it'll jump back to a syscall, and it'll have RDI set to bin shell, and it'll have end pointer and the ARD pointer both null. So to see what that looks like, really the code isn't too complex, even though it took a while to actually get here. Is this, ignore this. So we have ROP dancer, blah, blah, blah. We're starting, let's run it locally first. So the first thing we have to do is that buffer overflow. There's nothing too special about this, and we're just going to inject a single gadget here. First, we're going to overwrite the RBP on the stack, and then we're going to call this gadget. And this gadget, what it's going to do, so it does a pop RBP, which is just standard exit the frame sort of stuff. Then it's going to move RBP into RSP. And so this is our stack pivot. So at this point, our stack is going to be at an address we control. And so we're going to set it to, I said stage 2 address, which is the motivational letter. This is our 500 byte buffer. So now the stack is pointing at this 500 byte buffer. And then we're going to pop RBP. So it just takes another RBP. We don't really care about it at this point, and then it returns. Cool. At this point, I don't think this code has been executed. This gets executed at the end of the function. So we still, everything's kind of working normally. We haven't overwritten the stack or anything. At this point, it continues, and now we're going to, this is how you can create a sig return. Thankfully, Pwn Tools does all the heavy lifting for us, so we just say we want a sig return, and we get to start filling in the registers. And so, like I said, all these values are going to be popped off the stack and set to whatever we want. So just great for constrained environments where you don't have all the pop registers you need. So first, we set RAX to the syscall for execve. Then we set RDI to an address where bin shell exists. We're going to write bin shell to the start of the motivational letter, the 500 byte buffer. And so we know where that is, and we can just point it to there. We set both of these to null. One of these is argv, and one of these is end. And then we set RIP to some random syscall somewhere. I just found one right here. And so that way it's going to return. All the registers are set, and it's just going to call execve, and we should be set. So for the second payload, there's one other thing we need to do. So first we send bin shell, which we need for later. To call the SIGROP, or sorry, the SIG return, we need EAX to be equal to OXF, so 15. And to do that, thankfully there were gadgets. The first one was an XOR EAX, and then inc AL ret. So this is going to clear EAX and then increment it by 1, and then return. And then we do that 14 more times. And so that way AL will be equal to 15, so that when we call syscall, it'll actually work correctly. They will actually call the SIG return syscall. So at that point, we call the return, this syscall. It's going to read all those values on the stack, populate our registers, and then at that point, it'll return to this RIP where the syscall is, and it'll execute exec.ve, and at that point, we should have shell. So we can try running it. Let's do make Ubuntu 22, clear, Python 3, solve.py, and we do ls, and we can see we have shell. So let's try running it remotely. Where is it? This one. ls, there we go, and it says there's a selection criteria, so we can cat that out. There's a whole bunch of stuff, but we can see, here we go, and it says I want to be a rope dancer so bad. So yeah, very fun challenge. I love using those techniques. Yeah, cheers.